Okay, so I'm Wazir Muhammad. I'm assistant professor at Department of Physics, Florida Atlantic University. Today, I will talk about some artificial intelligence assisted decision support for individualized lung cancer radiotherapy. These are the outline of my today's presentation. So I will introduce a little bit about the statistics and role of radiation therapy for the lung cancer, big data and machine learning, and AI basics, data mining and machine learning applications for the lung cancer. And then I will discuss how we can assess the treatment decision through AI. And after that, I will conclude my presentation. So that's why I selected this lung cancer, because you can see here in the statistics, for example, here you can see this. This is the estimated cancer-related deaths, and it's on the top of the list. So the other are way smaller than just like from the lung cancer. And here you can see that the 13% counts is about for the new cases. So about 13% are the lung cancer patients in the newly diagnosed lung cancer patients. And here you can see these are different numbers for the lung cancers patients. So with respect to other, just like breast cancer and prostate cancer. So this is all about the lung cancer statistics. So that's very important, and we can see here that only 19% is the 5-year survival rate for the lung cancer. And if we diagnose it earlier, we can improve the statistic. But here it's 19%. So it's very late. This is a different, just like a tumor size, and according to the tumor size, the stages or the stages of the lung cancer is defined. So because I'm talking about these stages, because it is based on it's spread and based on the tumor size, so that if we deliver the radiation, so of course the tumor size will matter. Here, what are the current stage treatment strategies for the lung cancer? So surgery is one option. Systematic therapy, which includes chemotherapy, targeted therapy, and immunotherapy, and the next one is the radiation therapy. For the radiation therapy, we have different options. Three-dimensional conformal radiation therapy, we have intensity modulated radiation therapy, we have stereotactic body radiation therapy, or stereotactic ablative radiotherapy. And of course, we have some proton therapy as well. So these are all options for the treatment of the lung cancer. And based upon the stages and options, patient options, these techniques are applied in different combinations. Now, what are the goals for the modern radiation oncology to treat lung cancer? So the goal may be different. For example, sometimes to eradicate or shrink the whole tumor prior to the surgery. So before surgery, we apply those techniques. And sometimes just like after surgery, to remove any residual cancer tissues from the lung cancer, from the lung. And other one, just like the third goal, is to treat cancer spread to the other areas. So this is, if we understand the radiotherapy for the lung cancer, it's very complicated process and multi-step process. We have a doctor checkup that can just like assess the tumor status and stage of the lung cancer. Then we have treatment planning, and prescribed dose basis on the doctor checkup, and then we deliver the treatment. So this is very complicated process, and a multi-step processing. So these are some radiotherapy toxicity, which is related to the lung cancer treatment. So with radiotherapy, so for example, there are some short-term toxicity, which is normally start after second week. So these are tenderness in chest wall, sunburn, skin, fatigue, shortness of breath, trachea, lungs, sore throat, esophagus, etc. Some are the long terms, just like scars in the lung, fibrosis that will lead shortness of the breath, fever, cough, and we have irritations because of esophagus. In few weeks, we will have symptoms of the acute radiation in few months to the ears. So these are some radiation toxicity, and we have to take care of those toxicity while we are treating the patient with radiation. So the effectiveness is different, and it's not if we are treating this maybe the same patient with the same condition, but their location may be different, or their tumor size may be different, will respond differently. For example, if we have a lung cancer with a small cell, they will shrink quickly, and some may take up to weeks to months to disappear. Similarly, the leftover cancer cells after surgery will respond differently as compared to the whole tumor, to the solid tumor before surgery. And the radiation response will be different in combination with chemotherapy as well. But despite of we have a local tumor control with modern radiotherapy techniques or radiation oncology techniques, but still we have a considerable high local failure rate of radiotherapy. So these are some limitations. In most cases, the same radiation doses deliver irrespective of the tumor nature, just like the leftover cells, solid tumor before surgery. No consideration of the tumor characteristics and dynamics, significant variation in the quality and efficiency of the treatment, which depends on the experience and expertise of the clinicians and institutions. So how the staff of the particular clinic is expert or in their field. So it will particularly depends upon those expertise. And of course, the technology is another constraint. In some cases, there may be availability of the motion management, respiratory motion management. Some center may not have those. So then how we can handle in this situation. So this is the challenge. So clinical decision support tools, so that can suggest an individualized treatment. So that is a challenge for the AI and machine learning techniques. And that decision support tool will consider the patient health and the clinical conditions and consider previous optimized and successful treatment for similar patients. So that is the main thing, that how the previous treatment is successfully completed. And what will be the result? The result will be just like they will close the health disparities gap between rural and urban settings or smaller end. And how it will be possible, just like data mining in radiation oncology for the lung cancer. The data mining will be consist of the tumor dynamics and characterization of data sets, radiotherapy data sets, and patient follow-up data sets. So these three, the data mining will be just like consist of these three components. And of course, we have to apply machine learning or artificial intelligence techniques on this data, and that could be supervised machine learning, unsupervised machine learning, or reinforcement learning. So this now we have a lot of data. We know some data, just like we can keep it in daily practice, or we can view in daily practice. So on the basis of this data, some protocols are developed, and we know only those protocols. But most of the data is hidden, and it is not in use for future treatment. So we have a lot of treatments in past, but we are learning very less from that past treatment. And so that is the question. So can we make a connection between what we know and the rest? The data should have the big data should have those characteristics. The volume should be big. Velocity, there should be the speed at which the data is generated should be higher. Variety, the different type of the data, they must have all type of the cancer treatments, all type of the tumors, just like they have a lot of variety for that one. Veracity, just like the trustworthiness, the data should be accurate, and value, that will be, if we apply some machine learning techniques, the data itself is nothing, but it will be just like a space. It will occupy some space in your computer. But if we are able to apply some valuable tools on this data, then we can convert it into a value. These are some basics for the machine learning techniques. I will go over just like fast on this. So we have artificial intelligence that has been explored since 2015, and GPU makes parallel processing faster, cheaper, and more powerful. And big data pouring in, just like we have images, we have text, we have other just like mapping data. And deep learning, we have model data, decipher correlations, and make decision on basis of this this data. And for example, these are some time line for the development of the machine learning techniques and artificial intelligence. So this is just like the most recent is deep learning. So this is the most recent thing. So we have a supervised machine learning that includes decision tree, random forest, logistic regression, etc. We have unsupervised learning, which have a priori algorithm, k-means. We have reinforcement learning that just like AlphaGo, we have AlphaGo. And this is just like how supervised, unsupervised, and reinforcement learnings, or these are the three corners of the triangle. So here, in supervised learning, it learns from the known pattern. Unsupervised, just like learning unknown patterns, and the reinforcement learning that will generate the data, and also learning unknown patterns. So of course, this reinforcement learning is the true AI. So this is something about the artificial intelligence. So these are some opportunities of the AI in radiation oncology. For example, knowledge-based treatment planning and dose prediction, outcome prediction, just like survival, toxicity, reoccurrence. We have automated image re-registration and contouring, motion compensation and correlation, just like as I stated for the respiratory motion in lung cancer, tumor detection, segmentation and classification, radiomics and radiogenomics, big data analytics for clinical decision support. So we are basically focusing on the last one. So the other one are the subparts of this one. So this decision support will contain all those sections. So for example, data mining and machine learning applications for radiation oncology, just like related to the lung cancer. A lot of data is generated in radiation oncology. For example, we have imaging data, we have radiomics, we can get data from the images, we have pathological or biological data, and we have radiation therapy and physics dosimetry data. So these all, and we have just like some other data, which is such as patient data, patient clinical data, and financial data. So that's how we can generate a big data source and utilize it for the lung cancer treatment. So it will be a data source, a big data source for our machine learning techniques. So, for example, if we talk about uh, um, knowledge-based treatment planning, so you can see here some treatment plans, which is regularly created. So, for example, this is organ at risk, bladder, and the prostate cancer case, and here these are the triangles or the um, radiotherapy oncology group guidelines. So this dose should be less than these. So this is volume dose histograms for the prostate bladders, and this is parotid glands, DVH, and you can see here some treatments. Some treatment plans are sub quality treatments. Here is the applications of the artificial intelligence. So we can see here some, the red one says is the model predicted DVH, and the blue one represents the actual plan. So here you can see it in most of the cases, the model have predicted an efficient plan. So through this one, we can improve efficiency, reliability, and workflow of the treatment. So AI assisted lung cancer radiotherapy. So in this case, we are planning to test all these three types of the machine learning techniques. For example, deformation-based and probabilistic atlas dose predictions, fully connected neural network, and multitask deep neural networks, and convolutional neural network prediction. So we are planning just like to apply those techniques for the lung cancer. For example, in the deformation based and probabilistic atlas dose predictions, the techniques relies on 3 steps in which converting imaging and contouring data into descriptive data. After that, we deploy machine learning algorithm that that will utilize that imaging and contouring data. And finally, just like a deformable image registration algorithm that wraps and up prior dose volume to the novel patient geometry. So here you can see how it will work. So we have a novel patient here, and we have some machine, this deformation-based and probabilistic atlas dose prediction techniques. And here we will have some similar patient data, and from that one we can prescribe a novel dose to that patient. In the second case, we will have a fully connected neural network, and what it will do, that will model which will depends on the optimization theory in which inputs are fed forward to produce predictions, and it will the error that can be propagated, and it will train the model. And that is an alternative to the atlas-based method, which is used to predict those directly from the set of characterized features. So we have to characterize the features, and after that we can. And here you can see this is the individual neuron. We have some hidden layers here, and after that we can get some output here. So this is how we can use this fully connected neural network for the lung cancer treatment. The next one is convolutional neural network. So unlike to the other previously stated neural networks, the layers of the CNN have neurons arranged in 3D. So basically, those 3D are just like width, height, and depth, and that will give you a volumetric information. So basically, CNN will give us a volumetric information. But there is a disadvantage. It's just like the CNN-based models are very complex architecture, and those are difficult to train and require special hardware. So this is which may be not suitable for clinical use, because for clinical we need a computational efficiency for the to treat the patient, because we need to so this is good for research purpose, but we will see how feasible it will be for the clinical use. The most new one and the most appropriate will be reinforcement learning model. And here the reinforcement learning model is basically goal-oriented algorithm, and it learns by trials and error, and it will just like will be get rewarded or punished from the task that are performed. So for example, we will have an agent that will interact with the environment through actions and observations. So if this observation is close to the accurate or the real value, so it will be get rewarded. Otherwise, it will be punished, or just like the reward will be given on basis of the how far it is from the real value. So this here you can see this is the schematic of or the Markov decision process MDP chain. So this is how this one will be more realistic and more accurate one to apply for the lung cancer treatment. And this will be the architecture of the deep neural network nets for the lung cancer. So this will be the part, but the whole process will be we will apply this reinforcement model with in combination of this one. So we will have this data from the previous treatments and the current patient data, and we will input this data to the neural network, and then a personalized treatment suggestion will be run here, and this is how one neuron will work, and it will all based on this one. So if this one is for known patient, if this prescription is close to the most optimized treatment, it will be get rewarded. Otherwise, it will be punished. And on the basis of that reinforcement learning, we can create such a model for the lung cancer treatment. This how we can integrate it in a clinical flow. So we will have a new patient, we will have a data from the previous treatments from different hospitals. So, and then here is the deep reinforcement learning model, and here it will suggest some treatment planning. So it will be more based on the tumor dynamics of the current treatment, and it will be based on the previous successful treatment. So this is how we can integrate our model in the clinical flow. So here we are expecting a treatment planning that will be more close to the real scenario, or more close to the personalized planning, and more close to the optimized will be more optimized treatment planning for the patient. These are some challenges we can face during this project. So the data access, data standardization, of course, we will work on that one. Algorithm robustness, so that it can react to the different type of the data accurately. Data quality, how data is accurate, otherwise it will be garbage in and garbage out. And data privacy and security is, of course, very important for us. If we are we are just like got some data, so we will get some data, so this will be more important for us. And we need just like some challenges, so we need to share challenges, and that is that are administrative. Sometimes we will face that the administration will not be prepared to share the data. Some will be political issues, and some will be ethical and technical issues. So These are also the outlook conclusions. So big data in medicine is a gold mine. We can use it. We can utilize it. Open data access is the future, and standardization is the key to the data sharing in mining. So and AI augmented radiation oncology is coming. So this will be um, uh, more effective, and more, it could be more effective and more impactful for the treatment, even only not only for the lung cancer but also for other type of the cancer as well. So this is some final thought. So you are your data and your data is you. So this all we are, or just like the data, we have the data, and on the basis of that data we can predict something for ourselves. So uh, we have to take care about us and the data that we have in our body. So thank you, and if you have any questions, so